Good evening, everyone, and welcome to the Droning Professor. Tonight we're going to learn about Zhang, Heng, and the earthquake detector that shouldn't have worked. So, as you make yourselves comfortable, please take a moment to let us know where you're listening from, and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. Tonight, I want to tell you about a man who lived nearly 2,000 years ago. A man who built earthquake detectors shaped like wine jars, decorated with dragons and toads, who calculated pi to 5 decimal places, who mapped the stars with such precision that his work remained authoritative for centuries, and who wrote poetry so beautiful that it's still read today. A man who was simultaneously a mathematician, an astronomer, an engineer, a poet, a geographer, an inventor, a philosopher, and apparently had enough time left over to serve as the chief court astronomer and hold various governmental positions. His name was Zhang Heng, and if you've never heard of him, well, that tells us more about whose stories get told than it does about the magnitude of his achievements. Zhang Heng was born in the year 78 of the Common Era, during the Eastern Han Dynasty, in what is now Nanyang in Henan Province, China. To put this in perspective, he was born just a decade after the destruction of the Second Temple in Jerusalem, when the Colosseum in Rome was still under construction, and when most of Europe was what the Romans politely called barbarian territory. The Han Dynasty was at its height, a period often compared to the Roman Empire in terms of its technological advancement, administrative sophistication, and cultural flourishing. And let me tell you, the comparison is apt. While Romans were perfecting the art of the aqueduct, the Chinese were developing paper, inventing the wheelbarrow, and yes, creating seismoscopes that could detect earthquakes hundreds of miles away. But I'm getting ahead of myself. Zhang Heng came from a distinguished family. His grandfather, Zhang Khan, had been a governor, which in Han Dynasty terms meant the family had connections, education, and that peculiar kind of pressure that comes from having ancestors who accomplished great things. You know the type. Thanksgiving dinner where everyone casually mentions that great-great-grandfather was basically important, and what have you done lately? But unlike many people born into privilege who coast on their family name, Zhang Heng took that foundation and built something extraordinary. As a young man, Zhang Heng traveled extensively throughout China, which in the 1st and 2nd centuries was no small undertaking. We're not talking about hopping on a high-speed rail here. This was serious traveling, the kind that involved months on unpaved roads, river crossings that could kill you, and accommodations that made modern camping look luxurious. But this traveling was crucial to his education. He studied literature, he absorbed the landscape, he talked to people, and he developed what we might call today a systems-thinking approach to understanding the world. He didn't just see trees, he saw forests. He didn't just see stars, he saw the cosmos as a comprehensible system. Now, here's where Zhang Heng becomes really interesting, and where we need to understand the intellectual climate of Han Dynasty China. This was a civilization that had already invented paper in the year 105, just 27 years after Zhang Heng was born. They had bureaucratic examinations, extensive libraries, and a tradition of natural philosophy that emphasized careful observation and mathematical precision. Confucianism was the dominant philosophy, but there was also Taoism and legalism, and various schools of thought about how the universe worked. It wasn't a monolithic culture, it was a rich, argumentative, intellectually vibrant society where different schools of thought competed for influence. Zhang Heng positioned himself at the intersection of all these traditions. He was a Confucian scholar, yes, but he was also deeply influenced by Taoist ideas about the natural world. And he had something that transcended all philosophical schools, an insatiable curiosity about how things actually worked. Not how they should work according to some ancient text, but how they demonstrably, observably, measurably worked. In the year 100, when Zhang Heng was 22 years old, He began his formal education at the Imperial University in Luoyang, the capital. This wasn't like a modern university. There were no elective courses on underwater basket weaving or the history of the semicolon. The curriculum was focused, intensive, and centered on classical texts, history, mathematics, and astronomy. Astronomy wasn't just a nice-to-know subject. It was essential for the functioning of the state. The emperor's legitimacy was tied to his ability to maintain harmony between heaven and earth, which meant the court astronomers had to be able to predict celestial events with accuracy. If an eclipse happened that you hadn't predicted, that wasn't just embarrassing. It could be politically catastrophic. So when Heng studied astronomy, he wasn't pursuing some abstract intellectual interest. He was training for work that had real consequences. After completing his studies, Heng served in various governmental positions, but his real passion was always scientific inquiry. In the year 115, he was appointed as the chief astronomer, a position he would hold, with some interruptions, for much of his career. This was one of the most important positions in the entire bureaucracy. The chief astronomer was responsible for maintaining the calendar, predicting celestial events, interpreting omens, and advising the emperor on matters relating to heaven's will. It was part science, part politics, and entirely high stakes. Now let's talk about what Heng actually accomplished, because this is where things get genuinely mind-blowing. First, astronomy. Heng created a detailed star catalog that recorded the positions of 2,500 stars. Let me repeat that, 2,500 stars. By hand, without telescopes, without computers, without even particularly good timekeeping devices. He organized these stars into 124 constellations. He calculated that there were actually 11,520 stars visible from Earth, though he could only precisely measure the positions of those 2,500. For context, the most famous Western astronomer of antiquity, Ptolemy, who lived around the same time, catalogued about 1,000 stars. Heng catalogued more than twice as many. But Heng didn't just count stars like some kind of cosmic accountant. He developed a cosmological theory called the celestial sphere theory, or Huntian theory. This theory held that the Earth was like the yolk of an egg, suspended in the celestial sphere, which was like the white of the egg. The heavens rotated around the Earth, carrying the stars with them. Now, to our modern ears, this sounds wrong because we know the Earth rotates and orbits the Sun. But here's what's important. Heng's model was mathematically coherent, made accurate predictions, and was based on careful observation rather than mythology. He wasn't saying the gods put the stars there and they move because magic. He was saying, I have observed these patterns, I can model them mathematically, and I can predict future positions. That's science. Heng built an armillary sphere, which is essentially a model of the celestial sphere made of bronze rings representing the celestial equator, the ecliptic, the meridian, and other reference circles. This wasn't just a teaching tool, it was a precision instrument. And here's the really clever part. Heng built a water-powered version that rotated automatically, keeping pace with the apparent rotation of the heavens. This meant you could use it to tell time and to predict the positions of celestial bodies. He created, in essence, an analog computer for astronomical calculation, powered by the steady drip of water through a clepsydra, or water clock. The engineering required for this is substantial. You need to understand gear ratios. You need to control water flow with great precision. You need to understand the relationship between linear motion and rotational motion. And you need to be able to work metal with sufficient accuracy that your gears actually mesh properly. Heng did all of this in the 2nd century. But wait, as they say in infomercials, there's more. In the year 132, Heng invented what is generally considered to be the world's first seismoscope. Not a seismograph, mind you, which records the actual shaking, but a seismoscope, which detects that an earthquake has occurred and indicates the direction from which the seismic waves came. Now, you might think, okay, earthquake detector, that's useful, but you probably don't appreciate just how astonishing this device was. Picture a bronze vessel about 6 feet in diameter, shaped like a wine jar. Around the outside are 8 dragon heads, facing the 8 cardinal and intercardinal directions: north, northeast, east, southeast, south, southwest, west, and northwest. Each dragon holds a bronze ball in its mouth. Below each dragon sits a bronze toad with its mouth open, ready to catch a ball. Inside the vessel is a pendulum mechanism connected to a series of levers and triggers. When an earthquake occurs, even hundreds of miles away, the seismic waves traveling through the earth cause the pendulum to swing. This swing triggers a mechanism that causes one of the dragons to open its mouth, dropping its ball into the toad below with a loud clang. The direction of the dragon that drops its ball indicates the direction of the earthquake's epicenter. Let's pause here and appreciate what this means. Heng understood that earthquakes produce waves that travel through the earth. He understood that these waves have directionality. He understood that a pendulum suspended in a particular way would respond to these waves. And he was able to engineer a mechanism precise enough and sensitive enough to detect earthquakes that occurred hundreds of miles away and indicate their direction. In the year 138, 6 years after he built this device, an earthquake occurred. Zhang Heng's seismoscope indicated that it was to the west. But no one in Luoyang, the capital, had felt anything. Court officials were skeptical. Some mocked the device. Then, several days later, a messenger arrived from the west, reporting a significant earthquake in Longxi, about 300 miles away. Zhang Heng had detected an earthquake that no human in the capital could feel, and he had correctly identified its direction. After that, people stopped laughing. We don't have the original seismoscope. It was lost centuries ago. Modern attempts to reconstruct it based on descriptions in historical texts have had varying degrees of success, which tells you something about the precision of Zhang Heng's original engineering and the limitations of historical sources. But the principle is sound, and modern seismology confirms that the physics behind it would work. Now, let's talk about mathematics, because Zhang Heng wasn't content to just revolutionize astronomy and invent earthquake detectors. He also made significant contributions to mathematics, particularly in the calculation of pi. Pi, of course, is the ratio of a circle's circumference to its diameter, approximately 3.14159. In Zhang Heng's time, Chinese mathematicians had been working on calculating pi for centuries. The most common approximation was 3, which is, let's be honest, not very good. It's the kind of approximation you use when you're in a hurry and don't care very much. Some mathematicians had refined this to something like 3.14, which is better but still not great. Zhang Heng calculated pi as the square root of 10, which equals approximately 3.16228. Now this is actually slightly off. The true value of pi is about 3.14159. Zhang Heng's value is about 1.3% too high. But here's what matters. He derived this through geometric reasoning about the relationship between circles and squares, and he was working with the mathematical tools available in the 2nd century. The fact that he got within 1.3% of the true value is remarkable. For comparison, the ancient Egyptian approximation of pi from the Rhine papyrus around 1650 BCE was about 3.16, similar to Zhang Heng's, but arrived at more than 1800 years earlier through different methods. Zhang Heng also worked on calculating the volumes of spheres and other geometric solids. He developed formulas, he proved theorems, and he did all of this in a mathematical notation system very different from what we use today. Imagine doing calculus in Roman numerals, and you'll get some sense of the additional cognitive load involved. But here's what I want you to understand about Zhang Heng's mathematical work. It wasn't abstract. It was always in service of understanding the physical world. He needed to calculate pi because he was working on problems involving circular and spherical objects, the orbits of celestial bodies, the dimensions of his armillary sphere, the proportions of his seismoscope. His mathematics was a tool for doing science and engineering. This is why he's sometimes overlooked in histories of pure mathematics. His work was too applied, too practical, too useful. Now, you might be thinking, okay, so Heng was a genius polymath, I get it. But we haven't even talked about his work in geography yet. Heng created one of the earliest comprehensive maps of China. Again, this wasn't a casual project. Han Dynasty China covered an enormous area with diverse topography, climates, and peoples. Mapping it required collecting data from across the empire, reconciling different local accounts, understanding scale and proportion, and developing cartographic conventions for representing three-dimensional terrain on a two-dimensional surface. Heng's maps included mountains, rivers, roads, and administrative boundaries. He calculated distances between major cities. He understood the concept of a map legend. And he did all of this without any of the surveying tools we take for granted today. No theodolites, no GPS, no satellite imagery. Just reports from travelers, his own observations, and mathematical calculations. He also wrote a geographical treatise called Lingxian, or Spiritual Constitution, which described the dimensions of the earth and heavens according to his cosmological model. In this work, he calculated that the distance from the earth to the celestial sphere was 81,500 Chinese li. A li is a unit of distance equal to about half a kilometer, so he was suggesting the celestial sphere was about 40,000 kilometers away. This is, of course, wrong. There is no solid celestial sphere. But again, what matters is the methodology. He was trying to calculate cosmic distances using geometric reasoning based on observable phenomena. He was doing cosmology. And then, because apparently he had spare time, Heng was also a poet and literary figure. He wrote Fu, a form of Chinese poetry that's sort of like a prose poem, characterized by elaborate description, parallelism, and rhetorical flourish. His most famous work is The Two Capitals, a few that describes the Han Dynasty capitals of Chang'an and Luoyang. It's thousands of characters long, filled with vivid descriptions of architecture, ceremonies, natural beauty, and court life. It was enormously popular in his time and remained influential for centuries. Now, you might wonder why a scientist and engineer was spending time writing poetry. But in Han Dynasty China, this wasn't unusual. The ideal of the scholar official was someone who was both technically competent and culturally refined. You were supposed to be able to calculate the movements of the planets and compose elegant verses. This wasn't seen as a contradiction. It was seen as wholeness. The same sensibility that allowed you to perceive patterns in the stars allowed you to perceive beauty in language. Heng also wrote essays on political philosophy, commentaries on classical texts, and works on cosmology that blended scientific observation with philosophical reflection. He was critical of what he saw as superstition and insisted that natural phenomena could be explained through natural causes rather than divine intervention. This was a radical position in an age when omens, portents, and divination were taken very seriously at court. Heng didn't dismiss the importance of understanding celestial events, but he argued that they followed natural laws rather than expressing the anger or pleasure of heaven. This got him into trouble occasionally. Court politics in the Han Dynasty were Byzantine, pun intended, in their complexity. There were factions, rivalries, assassination plots, and power struggles. Heng, as the chief astronomer, had considerable influence because the emperor relied on him for information about celestial events. But this also made him a target. If he made a prediction that turned out wrong, his enemies could use it against him. If he contradicted the emperor's favorite soothsayer, he could fall out of favor. Heng navigated these waters with varying success. He lost his position as chief astronomer at least once, possibly twice, though he was later reinstated. The historical records suggest he was respected for his honesty and integrity, but sometimes frustrated with the political games. In his later years, he seems to have become somewhat disillusioned with court life. His later poetry includes themes of withdrawal, simplicity, and the superiority of rural life over urban corruption. He wrote about wanting to retreat from official duties and live as a hermit, though how serious this was versus conventional literary posturing is hard to say. Zhang Heng died in the year 139, at the age of 61. By the standards of the 2nd century, this was a respectable lifespan, though not extraordinary. He died in office, still serving as the palace attendant, a high-ranking position he had been appointed to a few years earlier. His influence, however, continued long after his death. His star catalogue remained the standard reference work for centuries. His cosmological theories were taught and debated. His seismoscope design was studied and imitated, though as far as we know, no one quite managed to replicate its sensitivity. His poetry was anthologized and memorized. His maps were copied and updated. For hundreds of years, if you were studying astronomy in China, you were studying Zhang Heng. But here's where the story gets complicated, and where we need to talk about why Zhang Heng isn't as famous as he should be. First, there's the language barrier. Zhang Heng wrote in classical Chinese, a language that's difficult even for modern Chinese speakers to read without specialized training. His technical works use specialized terminology that doesn't always translate well. Much of his writing has never been translated into English or other Western languages, and what has been translated often requires extensive annotation to be comprehensible to modern readers. Second, there's the loss of primary sources. Many of Zhang Heng's original works are lost. We know about them because later historians quoted from them or summarized them, but the complete texts are gone. His seismoscope is gone. His armillary sphere is gone. We have descriptions, we have second-hand accounts, but we don't have the artifacts themselves. This makes it harder to assess exactly what he accomplished and how. Third, there's the Eurocentric bias in how the history of science has traditionally been taught in the West. For centuries, the standard narrative went something like this. The Greeks invented rational inquiry. The Romans spread civilization. The medieval period was a dark age. And then the Renaissance and scientific revolution brought us modernity. In this narrative, China, India, the Islamic world, and other non-European civilizations show up mainly as sources of exotic goods or as places Europeans discovered and conquered. The idea that these civilizations had their own sophisticated scientific traditions that in some cases exceeded European achievements was largely ignored or dismissed. This is changing, thankfully. Modern historians of science recognize that science is a global endeavor and that major contributions came from many cultures. But the popular consciousness still lags behind. Ask a random person on the street to name a scientist from antiquity, and they'll probably say Archimedes or Aristotle. They probably won't say Zhang Heng, not because Zhang Heng was less accomplished, but because he's not part of the cultural narrative they learned. Fourth, there's the issue of attribution and credit. In traditional Chinese scholarship, there was less emphasis on individual achievement and more emphasis on working within and contributing to a scholarly tradition. Zhang Heng built on the work of earlier astronomers and mathematicians, and later scholars built on his work. This is normal in science. Newton famously said he stood on the shoulders of giants. But the Western tradition has tended to emphasize individual genius and dramatic breakthroughs, which makes it easier to tell stories about Galileo or Newton as solitary heroes revolutionizing science. Zhang Heng fits less easily into this narrative structure. And finally, there's just the problem of time and distance. Zhang Heng lived nearly 2,000 years ago, on the other side of the world from where most Western history was being written. The exchanges of information between China and Europe were limited and slow. By the time European Jesuits arrived in China in the 16th century and began seriously studying Chinese science, Zhang Heng had been dead for more than 1,300 years, and even in China, much of the detail about his life and work had been lost or simplified into legend. But let's talk about what Zhang Heng represents, because I think this is actually more important than any individual achievement. Zhang Heng represents the idea that science is not unique to any one culture or civilization. The scientific method, careful observation, hypothesis formation, mathematical modeling, experimental verification, emerges wherever people get curious about the natural world and have the tools and leisure to investigate it systematically. Ancient China had these conditions, and Zhang Heng was one of the people who took advantage of them. Zhang Heng also represents the idea that science and engineering are deeply practical endeavors. He wasn't doing astronomy for fun, though I suspect he found it fun. He was doing it because accurate astronomical predictions were necessary for maintaining the calendar, which was necessary for agriculture, which was necessary for feeding the population. He wasn't building an earthquake detector as an intellectual exercise. He was trying to save lives by giving early warning of seismic events. His work was always in dialogue with real-world needs. And Zhang Heng represents the possibility of being a whole person, someone who can calculate the movements of planets and write beautiful poetry, someone who can design sophisticated machinery and think deeply about philosophical questions, someone who serves in government and remains committed to honest inquiry. In our age of hyper-specialization, where we're all encouraged to pick a lane and stay in it, Zhang Heng's example is refreshing. He didn't pick a lane, he built roads. Now, I want to address something that might be bothering you. Am I romanticizing Zhang Heng? Am I making him out to be more impressive than he actually was? It's a fair question. Hero worship is a problem in the history of science. We like our stories about genius savants who single-handedly revolutionize entire fields. The reality is always more complicated. Zhang Heng had collaborators, assistants, predecessors whose work he built on, contemporaries who contributed ideas. He had access to the resources of the imperial court, which meant he could build expensive instruments that an independent scholar never could have afforded. He lived in a civilization with a long tradition of mathematical and astronomical inquiry, so he wasn't starting from scratch. All of this is true. But here's what's also true. Even accounting for all of that, Zhang Heng's accomplishments are extraordinary. The breadth of his expertise, the originality of his inventions, the precision of his measurements, the elegance of his mathematics, these things stand up to any scrutiny. If you took his seismoscope alone, that would be enough to secure his place in history. If you took just his star catalog, that would be enough. If you took just his calculation of pi, or his armillary sphere, or his maps, or his poetry, any one of these would make him a notable figure. The fact that he did all of them, and did them all well, is what makes him exceptional. Let me give you a thought experiment. Imagine if we discovered tomorrow that all of Zhang Heng's work had actually been done by 5 different people, and later historians had conflated them into one figure. Would that make the accomplishments less impressive? I don't think so. The work would still exist. The seismoscope would still be an ingenious invention. The star catalog would still represent hundreds of hours of careful observation. The poetry would still be beautiful. The fact that one person did all of this is remarkable, but the achievements themselves are remarkable regardless. There's a modern tendency to look at ancient science and feel a mix of admiration and condescension. We admire the cleverness, but we also know that much of it was wrong. Zhang Heng's geocentric cosmology was wrong. His calculation of pi was close but not exact. His maps, while impressive for their time, were wildly inaccurate by modern standards. His seismoscope, clever as it was, couldn't measure earthquake magnitude or provide the kind of detailed data a modern seismograph can. But this misses the point. Science isn't about being right. It's about being less wrong than you were before. It's about developing methods for investigating the world that allow you to make progressively better approximations of reality. Zhang Heng's cosmological model was wrong, but it was usefully wrong. It made predictions that could be tested. When those predictions turned out to be accurate, the model was confirmed. When they turned out to be inaccurate, the model could be refined. This is how science works. And here's something that might surprise you. Some of what Zhang Heng got wrong wasn't actually wrong in the way you might think. Take his geocentric cosmology. From an observational standpoint, if you're standing on the Earth, it does look like the stars are rotating around you. The heliocentric model doesn't feel more intuitive. In fact, it feels wildly counterintuitive. We don't feel like we're moving, so why would we think we're on a rotating planet orbiting the sun? It took precise observations of planetary motions over long periods and the development of more sophisticated mathematics before the heliocentric model became clearly superior. Zhang Heng had neither the observations nor the mathematics to make that leap. Given the data available to him, his geocentric model was entirely reasonable. This is an important lesson for thinking about science today. We often treat our current scientific understanding as if it's the final truth, when in fact it's just our best current approximation. Future scientists will undoubtedly look back at 21st century science and find things we got wrong, just as we can see what Zhang Heng got wrong. But that doesn't mean we're not doing real science, any more than Zhang Heng's errors mean he wasn't doing real science. The process is what matters. Let's talk about the specific historical context of the Eastern Han Dynasty, because this is crucial for understanding why Zhang Heng was able to accomplish what he did. The Han Dynasty, which lasted from 206 BCE to 220 CE, was one of the longest and most stable dynasties in Chinese history. The Eastern Han period, which is when Zhang Heng lived, ran from 25 to 220 CE. This was a time of relative peace and prosperity. The Silk Road was operating, bringing goods and ideas from as far away as Rome. Paper had been invented, making it easier to record and transmit information. The civil service examination system was developing, creating a class of educated administrators. The emperor during much of Zhang Heng's career was Emperor Shan, who reigned from 125 to 144. Emperor Shan was, by most accounts, a decent ruler but not a particularly strong one. He was influenced by court eunuchs and various factions, and his reign saw increasing corruption and political instability that would eventually contribute to the dynasty's decline. But for our purposes, what matters is that Emperor Shun valued scholarship and supported the work of people like Zhang Heng. The capital, Luoyang, was a cosmopolitan city with a population of perhaps 500,000 people. It had imperial libraries, astronomical observatories, workshops where craftsmen could build complex instruments, and a community of scholars who could discuss and critique each other's work. This infrastructure was essential. Zhang Heng couldn't have built his armillary sphere or his seismoscope without skilled metal workers. He couldn't have compiled his star catalog without access to historical records. He couldn't have refined his theories without colleagues to argue with. There's a tendency in popular culture to imagine ancient inventors as lone geniuses, working in isolation, having sudden breakthroughs. The reality is much more social and collaborative. Zhang Heng was embedded in a community of scholars and craftsmen. He read the work of his predecessors. He discussed ideas with his contemporaries. He had assistants who helped with observations and calculations. His genius lay not in somehow transcending this social context, but in making excellent use of it. The Eastern Han Dynasty was also a time of significant intellectual ferment. Different schools of philosophy competed for influence. There were debates about the nature of reality, the proper role of government, the interpretation of classical texts, and the methods for understanding the natural world. Zhang Heng was part of these debates. His insistence on natural explanations for natural phenomena, his use of mathematics to model the cosmos, his empirical approach to geography, all of these were interventions in ongoing arguments about how knowledge should be pursued. It's also worth noting that the Eastern Han Dynasty was facing real practical problems that science could help solve. Floods, droughts, earthquakes, these were constant threats to agricultural productivity and political stability. If you could predict when a flood was coming, you could evacuate people and save lives. If you could detect earthquakes quickly, you could coordinate disaster response more effectively. If you could keep an accurate calendar, farmers would know when to plant and harvest. Science wasn't just an intellectual luxury, it was a survival tool. Zhang Heng's seismoscope needs to be understood in this context. The Han Dynasty experienced numerous devastating earthquakes. The year 133, just a year after Zhang Heng invented his seismoscope, saw a massive earthquake in the capital region that killed thousands of people. These weren't just natural disasters. They were political crises. Earthquakes were interpreted as signs of heaven's displeasure with the emperor. If you could detect earthquakes early and determine their location, you could at least begin to coordinate a response, which might help stabilize the political situation. Similarly, Zhang Heng's astronomical work wasn't just about satisfying curiosity. The emperor's legitimacy depended on his ability to maintain harmony with the cosmos. If celestial events occurred that hadn't been predicted, it suggested the emperor had lost the mandate of heaven, so the pressure on court astronomers was immense. They had to be right, or people died. Not metaphorically, literally. If you made a prediction that turned out badly wrong, you could be executed for incompetence or disloyalty. This puts Zhang Heng's emphasis on accurate measurement and mathematical precision in a different light. This wasn't academic perfectionism, this was survival. He needed his star catalog to be as accurate as possible because his life might depend on it. He needed his armillary sphere to make correct predictions because his position at court depended on it. The fact that he was also interested in these things for their own sake, that he found the cosmos fascinating independent of political considerations, that's what makes him a scientist rather than just a court functionary. But we shouldn't ignore the practical pressures he was working under. Now, let's talk about some of the specific technical details of Zhang Heng's work, because I think this will help you appreciate just how sophisticated his thinking was. Start with his calculation of pi. The method Zhang Heng used was based on comparing the area of a circle to the area of a square that circumscribes it. If you have a square with sides of length 2 times the radius, the area of the square is 4 times the radius squared. The area of the circle inscribed in that square is pi times the radius squared. So the ratio of the circle's area to the square's area is pi divided by 4. If you can figure out this ratio, you can calculate pi. The challenge is measuring the area of a circle with sufficient precision. Zhang Heng's approach involved approximating the circle with polygons of increasing numbers of sides. As you add more sides to a polygon, it gets closer and closer to being a circle. If you can calculate the area of the polygon, you can get a good approximation of the circle's area. This is, by the way, essentially the same method that Archimedes used a few centuries earlier, though there's no evidence that Zhang Heng knew about Archimedes' work. It's an example of convergent evolution in mathematics, 2 smart people in different parts of the world solving the same problem with the same method. Zhang Heng's value for pi, the square root of 10, comes out to about 3.162. The true value is about 3.1416, so he's off by about 1.5%. For 2nd century mathematics, using the tools available, this is remarkably accurate. It's accurate enough for most practical purposes. If you're building a round building or designing a circular orbit, being off by 1.5% isn't going to cause catastrophic problems. Now, let's talk about his star catalog. Cataloging 2,500 stars involves several distinct challenges. First, you need to be able to identify individual stars consistently over time. This is harder than it sounds. On any given night, depending on the season, time, and weather, different stars are visible. Some stars are in clusters that are hard to distinguish. Some stars are very faint, and only visible under ideal conditions. You need to develop a naming system and a set of reference points so that this star tonight is identifiable as the same star you observed 6 months ago. Second, you need to measure the positions of these stars. Heng did this using angular measurements relative to the celestial equator and the ecliptic. Imagine the sky as a sphere surrounding the Earth. The celestial equator is the projection of the Earth's equator onto this sphere. The ecliptic is the apparent path of the sun across the sky over the course of a year. Any position on the celestial sphere can be described by 2 angles: its declination, which is like latitude, and its right ascension, which is like longitude. Heng measured these angles using instruments like the armillary sphere. Third, you need to account for the fact that the positions of stars appear to change over the course of the night as the Earth rotates. So you need to be able to either correct for this rotation or make your measurements at carefully controlled times. Heng did both. His water-powered armillary sphere rotated in sync with the apparent rotation of the heavens, which allowed him to track stars across the sky. And he made measurements at specific times carefully recorded so that he could compare observations made on different nights. Fourth, you need to organize all this data in a usable format. Heng organized his stars into constellations, which were traditional groupings that made it easier to navigate the night sky. He also created tables listing the positions and brightnesses of stars. This was a massive data management task. Remember, this is before databases, before spreadsheets, before even standardized paper sizes. All of this information had to be recorded by hand, on scrolls, in a way that was legible and accessible. The result was a star catalog that remained the standard reference work for Chinese astronomy for centuries. Later astronomers would add to it, refine it, and correct errors, but the basic structure Heng created endured. His armillary sphere was equally sophisticated from an engineering standpoint. An armillary sphere consists of several concentric rings, representing different reference circles on the celestial sphere. There's a ring for the celestial equator, a ring for the ecliptic, rings for the horizon and the meridian, and so on. These rings are mounted so that they can rotate independently, allowing you to model the apparent motions of celestial bodies. Building a stationary armillary sphere is challenging enough. You need to get the angles right, the rings need to be perfectly circular, and they need to rotate smoothly without binding. Building a water-powered armillary sphere that rotates automatically is significantly harder. You need a water clock that maintains a steady flow rate. This flow rate drives a wheel, which, through a series of gears, causes the armillary sphere to rotate at precisely the right speed to match the apparent rotation of the stars. The gear ratios need to be exact. If they're off by even a small amount, over the course of hours or days, your model will drift out of sync with reality. Heng got this right. His water-powered armillary sphere was accurate enough to be used for timekeeping and astronomical prediction. This is precision engineering at a level that wouldn't be matched in Europe for more than 1,000 years. The seismoscope deserves its own extended discussion because it really is one of the most remarkable inventions of the ancient world. Let me walk you through how it worked, based on reconstructions and historical descriptions. The device was about 6 feet in diameter, shaped like a large urn or wine jar. The outside was decorated with mountains, turtles, birds, and other ornate designs. This wasn't just functional, it was meant to be beautiful. Ancient Chinese scientific instruments often were. The 8 dragons were positioned around the vessel, each facing one of the 8 principal directions. Each dragon held a bronze ball about the size of a large marble in its mouth. Below each dragon sat a toad with its mouth wide open. Inside the vessel was the clever part. There was a pendulum, probably weighted and carefully balanced, suspended so that it could swing freely in any direction. This pendulum was connected to a mechanism of levers and triggers. When seismic waves reached the device, they would cause the pendulum to swing in the direction from which the waves came. This swing would trigger a lever that would release one specific ball from one specific dragon's mouth. The ball would fall into the toad below with an audible clang, alerting anyone nearby that an earthquake had been detected and indicating its direction. Now, here's what's particularly sophisticated about this design. Heng understood that seismic waves have different characteristics depending on whether they're primary waves, secondary waves, or surface waves. Primary waves travel faster but are less destructive. Secondary waves are slower but can be more damaging. Surface waves are the slowest but often the most destructive. A sensitive pendulum would respond primarily to the first waves to arrive, which would be the primary waves, giving an early indication of the earthquake's direction before the more destructive waves arrived. Modern seismologists have studied Zhang Heng's design and confirmed that the physics is sound. A properly designed pendulum would indeed respond to seismic waves in the way described. The challenge in reconstructing the device is that we don't know exactly how Zhang Heng designed his internal mechanism. The historical texts give us the general principle but not the detailed specifications. Modern reconstructions have used different approaches, some with a single central pendulum, some with multiple pendulums, some with different trigger mechanisms, and they work with varying degrees of sensitivity and accuracy. What we know for certain is that Zhang Heng's original worked. The historical record is clear about that. In the year 138, it detected an earthquake that no human in Luoyang could feel, and correctly indicated that the earthquake was to the west. That's not legend or mythology. That's documented historical fact. A device built in the 2nd century detected seismic waves that had traveled hundreds of miles underground and indicated their direction. That's extraordinary. Think about what this means in practical terms. In an age without telecommunications, without any way to quickly send messages across long distances, you had a device that could tell you something has happened to the west within minutes or hours of an earthquake occurring, rather than having to wait days for a messenger to arrive. This would allow the government to preposition relief supplies, to mobilize rescue teams, to prepare for refugees. It was disaster response technology 1,800 years ahead of its time. Let me shift now to Zhang Heng's geographical work, because this tends to get overshadowed by his more dramatic inventions, but is equally important in its own way. Geography in the Han Dynasty was essential for administration. The empire was vast, covering an area roughly comparable to the continental United States. It included deserts, mountains, fertile river valleys, and coastal regions. Different parts of the empire had different climates, different crops, different languages, and different customs. To govern effectively, you needed accurate information about distances, routes, terrain, and resources. Zhang Heng's maps were part of a long Chinese tradition of cartography. The Chinese had been making maps for centuries before Zhang Heng, but he brought to map-making the same mathematical precision he brought to astronomy. He understood the concept of scale, that a map is a proportional representation of reality. He understood the importance of consistent orientation. He developed conventions for representing different types of terrain. His maps included the major rivers of China, which were crucial both for transportation and for understanding flood risks. The Yellow River, in particular, was known as China's sorrow because of its tendency to flood catastrophically, sometimes changing its course and killing hundreds of thousands of people. Understanding the river's course, its relationship to surrounding terrain, and its flood patterns was literally a matter of life and death. Zhang Heng also mapped the roads and administrative boundaries of the empire. The Han Dynasty had an extensive road system, necessary for moving troops, collecting taxes, and maintaining communication between the capital and distant provinces. These roads weren't like modern highways. They were often just dirt tracks, but they were maintained and marked. Zhang Heng's maps showed where these roads went, how they connected different regions, and what the distances were between major cities. He calculated distances using the li, a unit of measurement that varied somewhat over time and by region but was roughly half a kilometer. When he said 2 cities were 1,000 li apart, he meant about 500 kilometers. These weren't estimates. They were based on actual measurements collected by surveyors and travelers. Heng compiled this data, corrected for errors and inconsistencies, and created maps that were usable for navigation and planning. His geographical treatise, Lingxian, went beyond mapmaking to address broader cosmological questions. How big is the Earth? How far away are the heavens? What is the relationship between terrestrial and celestial geometry? These might seem like abstract questions, but they had practical implications. If you understand the size of the Earth, you can better understand how longitude and latitude work, which helps with navigation. If you understand the relationship between the Earth and the celestial sphere, you can make better predictions about the apparent motions of celestial bodies. Heng calculated that the Earth had a circumference of about 100,000 li, which would be about 50,000 kilometers. The actual circumference of the Earth at the equator is about 40,000 kilometers, so Heng was off by about 25%. But consider, he was trying to measure the size of the planet without satellites, without the ability to travel vast distances easily, without even a clear understanding that the Earth was spherical. The fact that he got within 25% of the correct value is remarkable. He also tried to calculate the distance to what he called the celestial sphere, what we would call the distance to the stars. He came up with a figure of about 80,000 li, or 40,000 kilometers. This is, of course, wildly wrong. The nearest star is about 4 light-years away, which is about 40 trillion kilometers. But again, the methodology is what matters. Heng was trying to use geometric reasoning and observational data to calculate cosmic distances. He was doing the right kind of thinking, even if the specific numbers were off. Now let's talk about Heng as a literary figure, because this is an aspect of his life that often gets neglected when people focus on his scientific achievements. Heng wrote in multiple genres. He wrote fu, which were elaborate prose poems. He wrote shi, which were more conventional poems. He wrote essays, commentaries, and philosophical treatises. His literary output was substantial, though much of it is now lost. What survives gives us a window into his personality and his thinking that his technical works don't quite capture. His most famous literary work is The Two Capitals, or Jing Fu in Chinese. This is a fu, a poetic form that was extremely popular during the Han Dynasty. A fu typically involves elaborate description, ornate language, parallelism, and rhetorical flourishes. They were meant to be impressive, to show off the author's learning and linguistic skill. The Two Capitals describes the two Han Dynasty capitals, Chang'an, which was the capital of the Western Han Dynasty, and Luoyang, which was the capital of the Eastern Han. Chang'an was ancient, grand, and somewhat faded. Luoyang was newer, more vibrant, and where Heng actually lived and worked. The fu compares and contrasts these two cities, describing their architecture, their ceremonies, their markets, their people, and their relationship to the natural landscape. But the Two Capitals isn't just descriptive, it's also political and philosophical. Heng uses the comparison between the two cities to make arguments about the nature of good government, the relationship between past and present, and the balance between tradition and innovation. Chang'an represents the past, the foundation, the classical ideal. Luoyang represents the present, the practical reality, the need to adapt to changing circumstances. The tension between these two cities mirrors the tension in Han Dynasty culture between reverence for the past and engagement with the present. The language of the Two Capitals is dense, elusive, and difficult even for scholars of classical Chinese. Heng packs in references to historical events, classical texts, natural phenomena, and philosophical concepts. Reading it is like reading T.S. Eliot's The Waste Land or James Joyce's Ulysses. You need extensive footnotes to catch all the references, but the density of meaning is part of the point. It's meant to reward careful study. What's interesting from our perspective is that Heng brings to his poetry the same attention to detail he brings to his scientific work. When he describes the architecture of the palaces, he's precise about dimensions and proportions. When he describes natural phenomena, he's observationally accurate. His scientific sensibility and his poetic sensibility aren't separate. They're integrated. Heng also wrote poems that were more personal and intimate. Some of his later poems express frustration with court politics and a longing for a simpler life. There's a poem called Returning to the Fields, which is about leaving official service and returning to rural life. The imagery is of fields, streams, simple pleasures, and freedom from obligation. Whether Heng seriously contemplated retiring from court service, or whether this was just a conventional literary pose, is hard to say, but the sentiment is clearly expressed. There's also a political dimension to Heng's literary work. He wrote essays criticizing superstition and what he saw as the improper interpretation of omens. In Han Dynasty politics, omens were taken very seriously. A strange astronomical event, an unusual animal sighting, a vivid dream, any of these could be interpreted as signs of heaven's approval or disapproval of the emperor's actions. This gave tremendous power to those who could interpret omens, and it created opportunities for manipulation and fraud. Heng argued that many phenomena that were interpreted as omens were actually natural events that could be explained through natural causes. An eclipse wasn't heaven's anger. It was the predictable result of the movements of the sun and moon. An earthquake wasn't divine punishment. It was a geological event. This was a radical position, and potentially a dangerous one. If you argued that omens were just natural events, you were implicitly arguing that the emperor's actions couldn't be judged by heaven in this way, which could be seen as either pro-emperor or anti-emperor depending on the political context. Heng navigated these dangerous waters by positioning himself as a defender of rational inquiry and proper scholarship. He wasn't saying the emperor should ignore heaven. He was saying that heaven should be understood correctly, through careful observation and mathematical analysis, rather than through superstition and manipulation. This was a subtle but important distinction. His philosophical essays blend Confucian, Taoist, and what we might call proto-scientific thinking. From Confucianism, he took the emphasis on social harmony, proper governance, and moral education. From Taoism, he took the emphasis on natural processes, the importance of observing nature directly, and a certain skepticism about human constructs. And from his own observations and calculations, he developed a commitment to empirical evidence and mathematical reasoning. This philosophical synthesis is actually quite modern. Heng sounds in many ways like an Enlightenment thinker, someone committed to reason, evidence, and the power of human inquiry to understand the natural world. The fact that he was working in the 2nd century, 1500 years before the European Enlightenment, suggests that these ideas aren't uniquely Western or uniquely modern. They're human responses to the experience of investigating the world systematically. Let me talk now about Heng's influence and legacy, both in his own time and in later centuries. During his lifetime, Heng was respected and influential, though, as I've mentioned, he also faced political challenges. His position as chief astronomer gave him access to the emperor and significant resources, but it also made him a target for court factions. The historical records suggest he lost his position at least once, possibly because of political maneuvering by rivals, though he was later reinstated. After his death in the year 139, Heng's reputation grew. His star catalogue became the standard reference. His seismoscope was studied and admired, though apparently no one quite managed to replicate it successfully. His poetry was anthologized and taught. His maps were copied and updated. Later astronomers built on his work, refining his calculations and expanding his observations. During the Three Kingdoms period, which followed the collapse of the Han Dynasty in the year 220, China was divided and chaotic, but scholars continued to study Heng's work. During the Jin Dynasty, which reunified China in the late 3rd century, and the subsequent Northern and Southern dynasties period, Zhang remained a respected figure. His name was invoked as an example of scholarly excellence and technical skill. During the Tang dynasty, which lasted from 618 to 907, Zhang works were included in the imperial libraries and his methods were taught to court astronomers. The Tang was another golden age of Chinese civilization, comparable to the Han in terms of cultural and scientific achievement, and Tang scholars explicitly positioned themselves as inheritors of the Han tradition. Zhang was one of the figures they looked back to as a model. During the Song dynasty, which lasted from 960 to 1279, there was renewed interest in practical sciences and technology. Song scholars studied Zhang's inventions and tried to recreate them. There were several attempts to rebuild his seismoscope based on historical descriptions, with varying success. Song mathematicians studied his calculation of pi and his geometric methods. Song cartographers studied his maps and map-making techniques. And then came the Mongol invasions in the 13th century, which were devastating to Chinese civilization. Libraries were burned, scholars were killed, and much knowledge was lost. Some of Zhang's writings disappeared during this period. What survived did so because it had been copied multiple times and distributed widely enough that not all copies were destroyed. During the Ming dynasty, which lasted from 1368 to 1644, there was a conscious effort to recover and preserve classical Chinese learning. Ming scholars compiled encyclopedias, reprinted ancient texts, and wrote commentaries. Zhang's surviving works were included in these projects. But by this point, 1800 years after his death, much of the technical detail had been lost. What remained were his major achievements: the star catalogue, the seismoscope, the calculation of pi. But the nitty-gritty of how he actually did these things was increasingly unclear. When Jesuit missionaries arrived in China in the 16th century, they were astonished by the sophistication of Chinese science and technology. They had expected to find a backward civilization in need of European enlightenment. Instead, they found a civilization with a long and distinguished scientific tradition. The Jesuits studied Chinese astronomy, read Chinese mathematical texts, and sent reports back to Europe describing what they'd found. These reports had a significant impact on European thinking. The idea that China had a sophisticated scientific tradition independent of Europe was surprising and challenged European assumptions about the uniqueness of European rationality. Some European intellectuals began to argue for a more global understanding of human achievement. Others doubled down on European exceptionalism, arguing that whatever the Chinese had accomplished, Europeans had done better. In the 18th and 19th centuries, as European colonialism expanded and European military technology proved superior in conflicts with China, the narrative shifted. Chinese science came to be seen in Europe as quaint but inferior, evidence of a civilization that had stagnated while Europe had progressed. This was a self-serving narrative that justified colonial expansion and cultural imperialism, but it was also wrong. Chinese science hadn't stagnated. It had continued to develop, though in different directions than European science. And many Chinese achievements, including Zhang's, remained superior to anything Europe had accomplished until quite late. In the 20th century, as the history of science became more professionalized and more global, Zhang began to receive the recognition he deserved. Historians of Chinese science like Joseph Needham wrote extensively about him. His inventions were studied and reconstructed, his calculations were analyzed, his poetry was translated. He became recognized, at least among specialists, as one of the great figures in the history of science. In China itself, Zhang has long been a source of national pride. He's taught in schools, he appears in history textbooks, and his inventions are displayed in museums. There are statues of him, streets named after him, and scientific institutions that bear his name. The Chinese space program has honored him by naming a lunar crater after him. He's seen as an exemplar of Chinese scientific achievement, and a symbol of China's historical contributions to human knowledge. But here's what's interesting. Zhang Heng isn't just celebrated as a historical figure. He's also invoked in contemporary Chinese discussions about the relationship between science and culture, between tradition and modernity, between Chinese and Western approaches to knowledge. Zhang Heng represents the possibility of a distinctly Chinese scientific tradition that's both rigorous and culturally rooted. He's a reminder that science isn't the exclusive property of any one civilization. This has political dimensions in contemporary China. The Chinese government promotes Zhang Heng as part of a broader effort to instill national pride and to push back against the idea that China is merely catching up to the West. The message is, China has always been scientifically advanced. China's current scientific achievements are a return to historical greatness, not an imitation of the West. Whether you find this message inspiring or troubling probably depends on your political perspective, but it's worth understanding as context for why Zhang Heng matters today. Let me talk now about some of the specific technical mysteries and controversies surrounding Zhang Heng's work. First, there's the question of how exactly his seismoscope worked. We have descriptions from historical texts, but these descriptions aren't detailed enough to allow for a straightforward reconstruction. The main historical source is the Book of the Later Han, compiled in the 5th century, more than 300 years after Zhang Heng's death. This source tells us about the 8 dragons, the toads, the pendulum, and the general principle of operation, but it doesn't give us detailed specifications. Modern attempts to reconstruct the seismoscope have used different approaches. Some reconstructions use a single central pendulum that can swing in any direction. When the pendulum swings, it triggers one of 8 levers arranged around it, releasing the corresponding ball. Other reconstructions use a different mechanism involving an inverted pendulum that would fall in the direction of the seismic wave. Still others use multiple pendulums or more complex trigger mechanisms. These different reconstructions work with varying degrees of success. Some are quite sensitive and can detect small vibrations. Others are less sensitive and only respond to larger shocks. Some correctly indicate the direction of simulated earthquake waves. Others are less accurate. What this tells us is that while we understand the basic principle Zhang Heng used, we don't know the exact details of his implementation, and those details matter a lot for how well the device works. There's been some controversy about whether Zhang Heng's seismoscope could really have worked as described. Some skeptics have argued that the historical accounts are exaggerated or that later historians misunderstood what Zhang Heng actually built. But the weight of evidence suggests the historical accounts are essentially accurate. We know Zhang Heng was a skilled engineer. We know the physics is sound. We know there's a specific historical instance where the device worked as described. The most reasonable conclusion is that Zhang Heng really did build a working seismoscope, even if we don't know all the details of how he did it. Second, there's the question of Zhang Heng's calculation of pi. His value, the square root of 10 or approximately 3.162, is close but not exact. Some historians have argued that Zhang Heng might have had a better approximation but that it was lost or simplified in transmission. Others argue that 3.162 was indeed his best calculation. The evidence is mixed. What we do know is that later Chinese mathematicians did better. Zhou Changzi, working in the 5th century, calculated pi to 7 decimal places, getting 3.141596, which is extraordinarily accurate. Zhou Changzi explicitly built on Zhang Heng's work, so there's a direct lineage, but whether Zhou Changzi's achievement represents a refinement of Zhang Heng's methods or a fundamentally new approach is debated. Third, there's controversy about Zhang Heng's star catalog. The original catalog is lost. What we have are later copies and references in other texts. Some stars in these later versions are incorrectly positioned, which raises the question, are these errors Zhang Heng's, or are they errors introduced by later copyists? Given that Zhang Heng was known for his precision, and given that his armillary sphere would have allowed for accurate measurements, Most historians assume that most of the errors are from later copying, but we can't know for sure. There's also the question of whether Heng invented his armillary sphere independently, or whether he was building on earlier designs. The historical record shows that armillary spheres existed in China before Heng, so he didn't invent the basic concept. What he seems to have invented was the water-powered version that rotated automatically and the specific refinements that made his version more accurate than previous versions. But exactly what was original to Heng versus what he inherited from predecessors is hard to determine from the surviving sources. These technical mysteries and controversies are actually a normal part of the history of science. Ancient and medieval scientific texts often don't provide the level of detail we'd like. Devices are described in general terms rather than with exact specifications. Later copyists introduce errors. Different scholars interpret ambiguous passages differently. What's important is that we can reconstruct the general principles of Heng's work, verify that those principles are sound, and appreciate the magnitude of his achievements, even if we don't know every detail. Let me now address a question that might be bothering you. Why are we spending all this time on one person? History is made by millions of people, not by isolated geniuses. Heng had predecessors whose work he built on. He had contemporaries who contributed ideas. He had assistants who helped with observations and construction. He had access to imperial resources that independent scholars couldn't have dreamed of. Isn't focusing on Heng as an individual a distortion of how knowledge actually gets produced? This is a fair criticism, and it's one that historians of science take seriously. The great man theory of history. The idea that history is shaped primarily by exceptional individuals has been largely discredited. We know that social, economic, technological, and institutional factors are crucial for understanding historical change. No individual, however brilliant, can accomplish much without the right supporting context. But here's the thing. While we should be skeptical of great man narratives, we also shouldn't go so far in the other direction that we ignore individual achievement entirely. Heng really was exceptional. Yes, he built on the work of others. Yes, he had resources and support. Yes, he was part of a larger scientific community. But even accounting for all of that, what he accomplished was remarkable. Think of it this way. Thousands of people in Han Dynasty China had access to education, resources, and the opportunity to contribute to science. But only one of them cataloged 2,500 stars, invented a seismoscope, calculated pi to reasonable accuracy, built a water-powered armillary sphere, created comprehensive maps, and wrote influential poetry. That one person was Heng. There was something about his particular combination of intelligence, curiosity, technical skill, and persistence that allowed him to achieve what others didn't. Moreover, studying individuals like Heng isn't just about celebrating genius. It's about understanding what becomes possible under certain conditions. Heng's achievements tell us something about the state of science, technology, mathematics, and engineering in 2nd century China. They tell us about what the imperial bureaucracy valued and supported. They tell us about the relationship between practical problems and theoretical inquiry. They tell us about the transmission of knowledge across generations. Heng is both interesting in himself and interesting as a window into a larger world. Now let me talk about something that often gets overlooked, the sheer difficulty of what Heng did, not just intellectually but practically. Consider the physical challenge of astronomical observation. You're staying up all night, every night, in all weather, to observe stars. You're making measurements with instruments that are sensitive to temperature changes, humidity, and vibration. You're recording data by hand, by lamplight, probably while cold and tired. You're doing this for years, accumulating enough observations to identify patterns and calculate positions. This isn't just intellectually demanding, it's physically grueling. Or consider the challenge of building a water-powered armillary sphere. You need to source metal, bronze probably, which means copper and tin. You need to smelt this metal and cast it into precise shapes. You need to grind and polish surfaces so that gears mesh smoothly. You need to cut accurate threads so that adjustments can be made. You need to create a water clock that maintains a steady flow despite changes in temperature and water level. All of this requires not just knowledge but skill, patience, and the ability to work with craftsmen who have their own expertise and their own ideas about how things should be done. Heng wasn't doing this alone in some workshop. He was coordinating teams of people, astronomers to help with observations, metal workers to build instruments, scribes to record data, officials to provide resources and authorization. He had to explain what he wanted, convince people it was possible, manage conflicts, solve unexpected problems, and deliver results. These are skills that don't always get emphasized in histories of science, but they're absolutely crucial. And all of this was happening in a political context that was often hostile or at least indifferent. Court officials who thought astronomy was a waste of time. Rivals who wanted Zhang Heng's position and resources. Factions who opposed his scientific approach to interpreting omens because it threatened their political influence. Zhang Heng had to navigate all of this while also doing the actual scientific work. The fact that he succeeded, that he completed these massive projects, that his results were accurate enough to be useful, that his inventions actually worked, is a testament not just to his intelligence but to his determination and his political skill. Let me also talk about something that's often missed in discussions of Zhang Heng, his influence on how science was done, not just what science discovered. Before Zhang Heng, Chinese astronomy was certainly sophisticated, but it was often mixed with astrology, numerology, and cosmological speculation that wasn't clearly grounded in observation. Zhang Heng helped establish a standard where astronomical claims had to be backed up by precise measurements and mathematical calculations. You couldn't just assert that a celestial event had a particular meaning. You had to demonstrate that you'd accurately predicted it first. Similarly, Zhang Heng's approach to natural phenomena, the insistence that earthquakes, eclipses, and other dramatic events had natural causes that could be studied scientifically, helped establish a research program that later scientists could build on. He wasn't the first person to think this way, but he was influential in making this approach respectable and orthodox. His integration of poetry and science, of technical skill and cultural refinement, also established a model for what a scholar should be. The ideal Chinese scholar wasn't someone who knew only one thing. It was someone who had broad learning, multiple talents, and the ability to contribute to both practical affairs and cultural life. Zhang Heng exemplified this ideal, and later generations looked to him as a model. Now, as we approach the end of this lesson, I want to talk about what Zhang Heng means for us today, in the 21st century, nearly 2,000 years after his death. First, Zhang Heng reminds us that science is a human endeavor that transcends any particular culture or civilization. The scientific method, careful observation, mathematical modeling, experimental verification, emerges wherever human beings get curious about the natural world and have the resources to investigate it systematically. Zhang Heng was doing science in the 2nd century, using the tools and concepts available in Han Dynasty China, and what he accomplished was genuine scientific knowledge. Second, Zhang Heng challenges the narrative that science is uniquely Western. For too long, the history of science was taught as if it were primarily a European story, with occasional exotic contributions from elsewhere. This is false. Chinese scientists, Indian mathematicians, Islamic astronomers, and scholars from many other traditions made crucial contributions to human knowledge. Zhang Heng is one example among many, but he's a particularly striking example because his achievements were so varied and so impressive. Third, Zhang Heng demonstrates the value of interdisciplinary thinking. He didn't compartmentalize his interests into separate domains, astronomy over here, engineering over there, poetry somewhere else. He saw connections between these different areas. His poetry informed his science, His science informed his engineering informed his geography. This kind of integrative thinking is increasingly rare in our age of hyperspecialization, but it's also increasingly necessary for solving complex problems. Fourth, Heng shows us that practical problems can drive theoretical insights. He wasn't doing astronomy out of pure curiosity, though curiosity was certainly part of it. He was trying to solve real problems, maintaining an accurate calendar, predicting celestial events, detecting earthquakes. These practical challenges pushed him to develop better theories and better methods. This is a reminder that the distinction between pure and applied science is often artificial. The best science integrates both. Fifth, Zhang Heng's life and work raise important questions about how we evaluate scientific achievement. Should we judge historical figures by whether they got the right answers according to our current understanding? Or should we judge them by the quality of their methods and the reasonableness of their conclusions given the evidence available to them? I'd argue for the latter. Zhang Heng's geocentric cosmology was wrong, but his method, careful observation, mathematical modeling, making predictions and checking them against reality, was absolutely right. That's what matters. Sixth, Zhang Heng reminds us that scientific instruments and technologies aren't just neutral tools, they embody particular ways of understanding the world. His armillary sphere wasn't just a device for tracking stars, it was a physical manifestation of his cosmological theory. His seismoscope wasn't just an earthquake detector, it was built on a particular understanding of how seismic waves propagate. When we study these instruments, we're studying not just technical devices, but ways of thinking. Seventh, Zhang Heng's integration of science and governance is worth thinking about. He wasn't an academic working in isolation from society. He was a government official whose scientific work had direct practical and political consequences. His astronomical predictions affected state policy. His earthquake detector was a tool of disaster management. His maps shaped administrative decisions. This is a model of science that's deeply engaged with society, for better and worse. The for worse part is worth acknowledging. When science is closely tied to political power, there's always the risk that scientific conclusions will be distorted by political pressure. Zhang Heng seems to have maintained his integrity, insisting on accurate observations and honest interpretations, even when they were politically inconvenient. But the temptation to tell rulers what they want to hear must have been enormous. This is a challenge that scientists working in government contexts still face today. Eighth, Zhang Heng's work reminds us that the history of technology isn't a simple story of linear progress. The seismoscope he built in the year 132 was not improved upon for more than 1700 years. That's not because later civilizations were stupid or backward. It's because the knowledge of how to build such a device was lost, and because the particular combination of circumstances that made its invention possible, the resources, the institutional support, the intellectual climate, didn't recur. This should make us humble about our own technological achievements. We like to think that once something is invented, it's permanent, that human knowledge only accumulates and never gets lost. But that's not true. Knowledge can be lost. Entire technologies can be forgotten. Civilizations can collapse and take their learning with them. The fact that we know more now than Zhang Heng did isn't inevitable. It's the result of thousands of years of work by millions of people to preserve, transmit, and build on knowledge. We're the beneficiaries of that work, but we're also responsible for continuing it. Ninth, Zhang Heng's story illustrates the importance of documentation and record-keeping. Much of what we know about Zhang Heng comes from the Book of the Later Han, compiled centuries after his death. If the compilers of that book had decided Zhang Heng wasn't important enough to include, or if that book had been lost, we might know almost nothing about him. The accidents of preservation shape whose stories get told and whose get forgotten. This has implications for how we think about contemporary science. What we're doing today that seems important will only be remembered if someone takes the trouble to document it, preserve those documents, and pass them on to future generations. And what we think is trivial might turn out to be crucial. We can't predict what future historians will care about, which means we have a responsibility to document broadly and preserve carefully. 10th, and finally, Heng reminds us that individual human beings can make a difference. Yes, he was part of a larger social and intellectual context. Yes, he built on the work of others. Yes, he had advantages of birth, education, and access to resources. But even acknowledging all of that, Heng's individual contributions were real and significant. He saw further than his contemporaries. He asked better questions. He devised cleverer solutions. He worked harder and thought more carefully. These individual qualities mattered, and they still matter today. Let me end by considering a counterfactual question. What would have happened if Heng had never lived? Would someone else have invented the seismoscope? Would someone else have catalogued 2,500 stars? Would someone else have calculated pi with similar accuracy? Maybe. History is full of examples of multiple discovery, where different people in different places come up with similar ideas around the same time. This suggests that many scientific discoveries are, in some sense, in the air. When the right conditions exist, someone will make the discovery. So perhaps Heng's specific contributions weren't essential. Someone else would have done similar work sooner or later. But I don't think that's quite right. Yes, the general trajectory of Chinese astronomy would probably have been similar without Heng. Someone would have improved star catalogs. Someone would have built more accurate astronomical instruments. Someone would have worked on earthquake detection. But the specific achievements, the particular elegance of Heng's seismoscope design, the particular precision of his star positions, the particular integration of poetry and science in his writing, these were unique to Heng. A different person would have done things differently, and human knowledge would have taken a somewhat different path. Moreover, even if Heng's discoveries were somehow inevitable, the fact that he made them when he did, in the way he did, mattered for everyone who came after him. Later, astronomers built on Heng's star catalog, not on some hypothetical catalog that someone else might have made. Later, engineers studied Heng's seismoscope, not some other design. The specific path that scientific knowledge takes, the specific order of discoveries, the specific formulations of theories, all of this affects what becomes possible next. History is path-dependent, and individuals affect the path. So Heng mattered. His life and work made a difference. Nearly 2,000 years later, we can look back and see that difference clearly. And if we're lucky, if we work hard enough and think carefully enough and remain curious enough, maybe someday people 2,000 years in the future will look back at what we did and find it worth remembering. Let me close with one final thought. Heng lived in a world that was, in many ways, very different from ours. No electricity, no telecommunications, no modern medicine, no computers. Life expectancy was short, infant mortality was high, and most people never traveled more than a few dozen miles from where they were born. By material standards, even the wealthy in Heng's time lived lives that we would consider impoverished. But in other ways, Heng's world wasn't so different from ours. People were curious about how things worked. They looked up at the stars and wondered what they were. They experienced earthquakes and wanted to understand them. They valued beauty, poetry, and cultural refinement. They tried to make sense of their place in the cosmos. They worked to solve practical problems and to leave something of value for future generations. Heng was, in the end, a human being doing human things, trying to understand the world, trying to make life better for his community, trying to create something beautiful and lasting. The fact that he succeeded so remarkably is inspiring. But the fact that he tried it all, that he devoted his life to inquiry and creation rather than just to personal comfort and survival, that's what makes him truly admirable. We are, all of us, Heng's heirs. We benefit from the accumulated knowledge, of 2,000 years of human inquiry, including Zhang Heng's contributions. We use technologies that build on principles he helped establish. We live in a world shaped by the choices of people like him. And we have the opportunity, if we choose to take it, to continue the work he began, to observe carefully, to think rigorously, to create beautifully, and to leave something of value for those who come after us. Zhang Heng died in the year 139, but his legacy lives on. Every time we look up at the stars and wonder, every time we try to understand a natural phenomenon through careful observation and mathematics, every time we build an instrument to extend our senses and measure what was previously immeasurable, we're walking a path that Zhang Heng helped clear. So tonight, when you go outside and look up at the sky, think of Zhang Heng. Think of him standing in the observatory in Luoyang, nearly 2,000 years ago, carefully measuring the positions of stars. Think of him adjusting his water-powered armillary sphere, checking that the flow rate was just right so the mechanism would turn smoothly. Think of him listening for the clang of a bronze ball falling from a dragon's mouth, indicating an earthquake hundreds of miles away that no human could feel. Think of all the hours he spent observing, calculating, building, writing. Think of all the challenges he faced. Technical problems, political obstacles, the sheer difficulty of doing precise work with imperfect tools. Think of his curiosity, his persistence, his refusal to accept easy answers when better answers were possible. And then ask yourself, what will you build? What will you observe? What will you calculate? What will you leave behind? Zhang Heng had no idea that people would still be talking about his work nearly 2,000 years after his death. He couldn't have imagined the world we live in now, with its computers and satellites and global communications. But he did the work anyway, as carefully and precisely as he could, because it was worth doing. That's the lesson I want you to take from tonight. Zhang Heng's specific achievements, the seismoscope, the star catalog, the calculation of pi, these are remarkable, and they deserve to be remembered and celebrated. But the deeper lesson is about the value of careful work, rigorous thinking, and the integration of scientific inquiry with cultural and ethical commitments. Zhang Heng wasn't just a brilliant scientist, he was a complete human being who brought intelligence, creativity, and integrity to everything he did. In an age of increasing specialization, where we're encouraged to focus narrowly on one skill or one field, Zhang Heng reminds us that breadth is possible and valuable. You can be a scientist and a poet. You can solve practical problems and contemplate philosophical questions. You can serve in government and maintain your intellectual integrity. You can contribute to human knowledge and create things of beauty. You can, in short, be fully human. In an age of rapid technological change, where last year's breakthrough is this year's obsolescence, Zhang Heng reminds us that some achievements endure. His seismoscope may be gone, but the principle behind it is still sound. His calculation of pi may have been superseded, but his geometric method is still taught. His star catalog may have been improved upon, but his basic observations were accurate. Quality work lasts. In an age of global connectivity, but also of cultural misunderstanding, Zhang Heng reminds us that brilliance appears in all cultures and all civilizations. The capacity for rigorous thought, for careful observation, for creative invention, these are human universals, not the property of any particular group. When we study someone like Zhang Heng, we're not just learning history, we're challenging our assumptions about whose stories matter and whose achievements count. And in an age of environmental crisis, political instability, and existential risk, Zhang Heng reminds us that human beings have always faced challenges and have often responded with ingenuity, courage, and creativity. The Han Dynasty eventually collapsed. Zhang Heng lived through political turmoil, natural disasters, and social upheaval. But he kept working. He kept observing. He kept building. He kept writing. He did what he could, with what he had, where he was, and it mattered. So, as you leave tonight, carry Zhang Heng with you. Carry his curiosity, his precision, his creativity, his integrity. Carry the knowledge that one person, working carefully and thinking rigorously, can contribute something of lasting value to human civilization. Carry the inspiration of someone who looked at the stars and the earth, who observed and measured and calculated and built, who wrote poetry and prose, who served his community and pursued truth. Heng lived nearly 2,000 years ago, but in the most important ways, he's still with us. His spirit, the spirit of inquiry, of precision, of integration, of service, continues in everyone who looks at the world and asks, how does this work? And then commits to finding out. The stars Heng catalogued are still there, still moving in their predictable patterns. The earth still shakes with earthquakes that follow natural laws. Pi is still the ratio of a circle's circumference to its diameter. The natural world Heng studied so carefully is still here, still waiting to be observed and understood. And we are still here, Heng's descendants in spirit, if not in blood, continuing the work of understanding this mysterious, beautiful, complex cosmos we inhabit. Good night. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.